When you watch an industrial robot thread a needle or weld a seam, the physical movement appears perfectly fluid. But behind that smooth physical motion is a rigid, unyielding framework of abstract mathematics. To control that hardware, engineers use a mathematical process called forward kinematics. It is the calculation required to take the internal angles of a robot's motors and output the precise global location and orientation of its end effector, or gripper. Here is a standard planar robot arm: a fixed base, 3 motor joints, 2 physical links, and a gripper. We know the exact degrees each motor rotated. The spatial problem is calculating where exactly that puts the gripper on the absolute global grid. If you try to calculate this using standard trigonometry, the geometry tangles quickly. When multiple joints rotate simultaneously at the end of moving links, we need a mathematical framework that scales without breaking down. We start by defining our hardware. Our first physical link is exactly 2 units long, and our second link is 3 units long. To calculate how these fixed lengths interact with the moving motors, we have to attach a localized, moving coordinate frame to every single joint. There is a strict rule for assigning these frames. The local x-axis of any moving frame must lock perfectly parallel to the physical link connected directly to it. By isolating each joint inside its own coordinate system, we can evaluate its movement entirely on its own, completely ignoring the rest of the robotic arm. We are breaking a highly complex global positioning problem into a series of simple, relative steps from one local frame to the next. The homogeneous matrix bridges our coordinate frames. The upper left 2x2 submatrix strictly tracks rotation. Beside it, this 2x1 vector handles physical linear displacement. Finally, the bottom row of zeros and a 1 forces a uniform 3x3 square. A standard 2x2 matrix can only compute rotation. Expanding the footprint to a 3x3 structure allows us to calculate rotation and linear displacement simultaneously. Our process is simple. We will build one custom matrix for each distinct step of the robot's kinematic chain. This specific architecture neatly packages distance and angle into pure algebra, making it the ideal vessel for robotics. Let's build matrix H1, mapping the fixed global base to our very first moving frame, M1. The fixed base and M1 origins share the exact same physical location. With 0 gap, the displacement vector populates with 0 in x and y. The motor pivots M1 100 degrees, dropping that value directly into our rotation submatrix. Matrix H1 is complete. It encodes the exact action of the first motor, serving as a purely rotational launchpad with no linear translation. Next, we map the jump from frame M1 across the first physical link to the second joint, frame M2. The physical link stretches exactly 2 units down M1's localized x-axis. This localized displacement of 2 in x and 0 in y loads into the translation vector for matrix H2. Now we calculate the rotation. Counterclockwise movement is universally positive. Tracing the full counterclockwise path from M1's x-axis to M2's x-axis reveals a sweep of 330 degrees. We drop that 330-degree input directly into our rotation submatrix. Matrix H2 is now complete. It is completely blind to the fixed global base. It only knows its relative, isolated relationship to frame M1. Finally, we map frame M2 across the second link to the gripper, giving us frame M3. The second link's displacement is exactly 3 units along M2's local x-axis. We populate the displacement vector for our third matrix H3 with 3 and 0. We now need the final joint rotation required to orient the gripper. Tracing the counterclockwise path from M2's x-axis to M3's x-axis yields a 280-degree sweep. That 280-degree value slides into our final rotation matrix. The setup is done. We have translated the physical reality of scattered joints and links into 3 clean, isolated algebraic packets. With our 3 matrices complete, we execute a sequential matrix multiplication. We multiply them together from base to gripper. A foundational property of linear algebra states that multiplying any sequence of homogeneous transforms will always output another perfectly valid homogeneous transform. This newly minted H-total matrix bypasses the middle joints entirely. It draws a direct mathematical line connecting the fixed base straight to the gripper. Matrix multiplication acts as the mathematical equivalent of physically snapping the robot links together into a single, unified system. To find the answer, we look at the displacement vector inside our new H-total matrix. The output reads 0.68 and 4.79. Translating those numbers back into physical reality, the gripper is exactly 0.68 units right and 4.79 units up from the base. The orientation of the gripper is contained in H-total's rotation submatrix, which cleanly captures the linear addition of our 100, 330, and 280 degree inputs. You can now take any theoretical object in the gripper's local frame, multiply it by this H-total matrix, and immediately know its exact coordinates on the global grid. This absolute mathematical certainty allows control software to confidently drive physical hardware to exact targets in the real world, entirely without line of sight. Forward kinematics requires zero guesswork. It is the process of building a continuous mathematical chain, transforming isolated, localized mechanics into absolute spatial awareness.